Hi everybody, welcome back. Well, it's a cold, wet, rainy weekend, and I can't think of any better time to spend some time at the bench when it's like that out. So what we're going to look at today is a piece of test equipment. I have a friend that donated a whole bunch of old equipment like this from a former repair shop. I was an individual, I guess, who had a little TV or radio repair shop many years ago. And he didn't know what any of it was, and neither did I, and he just loaded it all in his pickup truck and brought it over here and dropped it off one day. And several of the pieces of test equipment are very interesting, and this is one of them. This is a Precision Electronic Model 200 signal tracer. So it's similar to our ICO 147, and you've seen those a lot on my videos, and Heathkit and many other companies have made these things. And essentially what they're used for is tracing both RF modulated signals and audio signals through a radio or through a small amplifier or something. They're really handy to have on the bench. Now there's many different versions, and essentially all any of them is, in their most basic form I guess, is just a really high gain amplifier and a detector circuit that can strip the audio modulation off of an RF carrier. So that's really all they do. Now, what more advanced signal tracers like the ICO 147 and so forth, they have a noise function where they can check for noise signatures on carbon resistors and leaky capacitors and things like that. And they also have, some of them will have a watt meter, so they can actually measure the wattage being drawn by a supply. There's a little outlet on there, and they have a little eye tube. They're all fancy things, but really, if all you're trying to do is chase a signal through a radio circuit, especially in the IF section or something like this basic one is all you need. Now, a long time ago, I didn't have a signal tracer, so I made one of my own. And I just made a wooden box and just took a piece of aluminum off of a plastic Radio Shack project box case and an old car speaker. And I took a Radio Shack project box, an old transformer off of an old tuner that I had a long time ago, and a output tube and one gain tube. This one doesn't have as high of gain as the ones with the pentodes, but it works. And for what I was doing, it actually worked. It still does. So anyway, I like this one, and the reason I like it is because it has this, now the probe is missing from it, but the insides of the probe still exist. As you can see, here's the ground lead, and then you can see there's a vacuum tube here, and this one happens to be a 6C4, which is just a single triode tube. And it has, you can see where the wire was cut off the end. That actually went to the probe tip. And all this thing is acting as is a diode. And if my memory serves me correctly, and correct me if I'm saying this wrong, I might be wrong, but I believe all this is called is a grid leak detector circuit. And essentially all it's doing is it's using this triode as a diode. And it has it's a lot more sensitive than a regular, for instance, even a germanium 1N34 diode, which is what they typically use in these signal tracers. So we're going to try to revive this and use it. That's one of the things we want to do in this video. I'm not going to try to plug it in. You can see how old and crusty it is. I want to just take it apart and see what's inside. I was unable to find a service manual for this, but I was able to find a service manual for a couple of models newer than this, like I think it's a 201 or a 205 or something. And I think they're all very similar. So we should be able to figure it out from what we have. So in some test equipment, especially meters, like some of the analog meters and things, one of the specifications that that we specify, sometimes you see, is crest factor. But on this one, I think we're going to coin a new one, which is crust factor. Yeah, it's kind of crusty in there. But I think it will clean up. Looking at this now, obviously it has been well used, and all of this equipment I got was like that. And I actually got an ICO, I think what was it, ICO 160 or something like that, oscilloscope, and I completely restored it. It turned out beautiful. We'll have to do a video on that sometime. So it is fixable equipment, but it was used. I mean, it was used. This person used this to make a living, and then I think when he retired, it ended up sitting for a long time. Now, this transformer to me doesn't appear to be original. As you can see, the holes right here where some of the wires came through originally, you can see some of the mounting holes on the bottom. So obviously the transformer at some point in time must have failed, and the owner must have replaced it with this one, because you can see how large this transformer, you don't need this great big transformer for this. So he probably harvested it from another piece of equipment somewhere. It uses a 5Y3 rectifier, which is just a dual diode, a 6K6 pentode output tube, which is, just these were pretty common at this time, and a 6SJ7, which I don't remember if it's 6SJ7 is a triode, which would be half of a 6SN7, or if it's actually a pentode tube. I'll have to look it up. I'll put it up on the screen. But that's it. That's the whole thing. I also kind of like the notes that this person put in here when he worked on it. You can see he put a little diagram of what this switch does and how it works. And he marked from the bottom the tubes that are for each socket. You can see that the across the line capacitors are definitely shot completely, and they'll need to be clipped out. We have one electrolytic can capacitor down here, and then we have these two electrolytics right here, which are paper capacitors. Those will all have to go. But we're going to have our work cut out for us on this one. And I think the first thing we need to do is get an accurate diagram of how this thing is put together. All right, let's take a look at this for a second, if we can. Looking in the receiving tube manual, they skip over 6SJ7, and if you look in here, they list it in here, and it says refer to the chart at the end of the section. So when you see that, you go to the end of this section, and you have the characteristics chart. And if you look in here at 6SJ7, and it shows the outline, terminal diagram, and so forth. And you can see it's a sharp cutoff pentode. So it is a pentode tube. So it's high gain. And that's what we thought it would be. And then also they list the diagram, terminal diagram as being diagram 8N. And if we jump over to the back of the book and look at terminal diagram 8N, here's our pin numbers, and here's our terminals, what they are. So you can see the shield is on pin 1, heater is pin 2 and 7, and then your G3, G1, cathode, and G2, and plate. You can see they're all marked like that. So some of the tubes in these manuals, they'll do the shortcuts like that. And you can still download, if you go online, you can download the full data sheet, but it's just this book doesn't have that. So this is RC30, which is a later version of the tube manual. And if you go back to some of the older manuals, it'll have a more complete layout like you're used to seeing. So just interesting stuff. Okay, before I try to look for a schematic that matches this particular circuit, I'm going to write down the complement of vacuum tubes that are used in here. I am also, since this transformer has been replaced, I want to get a couple of measurements of that. So in order to do that, we're going to remove all of the tubes, just like this. We don't even know if these tubes are good or not. We don't care at this point in time. We're going to remove those. We're going to plug this into a current limited supply, and then we're going to measure the output voltage. Now, if we put this on a dim bulb tester, the bulb will not significantly drop the mains voltage. It'll drop it a little bit, but not a whole ton, as long as there's no current being drawn. So what we're, very low current, just the quiescent current that the, transformer core will cause, and the windings themselves. But bottom line, we're going to clip these out because these are probably shorted, and then that will kind of isolate this transformer from the rest of the circuit, and we can take some measurements. All right, we've removed these two capacitors, and I have plugged this device into the dim bulb tester, and I just have like a 40-watt bulb connected right now. And I'm going to turn it on here in a second. I have to make sure that the power switch for the unit is turned on, which I believe is right here. I'll turn that on. And let's flip the switch, and we'll see if the bulb lights up first. We shouldn't get huge, if nothing's shorted, the bulb should stay dim. So I'll just focus you there to a second. This is the bulb I'm using. You can see there's essentially nothing. Now, that could be that there is no voltage getting to the transformer itself, but it could also mean that the current is just that low. So the first thing we want to do is measure our mains getting into there. And I'm going to have to reposition the camera because I can't reach. Okay, here we go. So power is on. So I'm going to go from here to here. You can see we have 112 volts. So it's a little bit lower, of course, because of the bulb. And going into the power transformer, we have one lead here and one lead here, and we have power going into the transformer. So there's very minimal current. So we should see an output. Excuse me. So here is our filament leads, which will be on pins 2 and 7 of the rectifier tube. And you can see we only have about 2.8 volts, and that's because we have low voltage going into the transformer right now. There's a little bit of a drop there. So that's low. And if we look at, I don't know how he has this connected, looks like we have ground here. And if I go to either side of the secondary of the transformer, I have 350 volts on that side, and I have 350 volts on that side. And I should probably have about 700 volts across it, and I do. And that's a lot of voltage for this circuit. So that right there tells me this transformer probably shouldn't be used in this, because most of these circuits don't run quite that high. Remember, I'm running through a current limited supply right now. You're not getting your full 125 volts to the input of the transformer, and you're already over 350 volts output. Now I know that's unloaded, I get all that, but that's your peak voltage. Your peak unloaded voltage will be very similar to your rectified voltage when there is no current flowing from the circuit. So at least until the tubes warm up, that's the kind of voltage you'll see on those capacitors. And if it's 350 volts RMS, then your peak voltage is going to be 1.414 times that. So you're going to have a power supply that's floating somewhere between 360 and 400 and some volts in the output. So that transformer does not belong in here. It's not the correct one. Now, maybe he got away with it, but if you look, these capacitors are rated only at 400 volts. So let me shut this off. Let's look at something else. Okay, well, maybe Tony stands corrected, because if you look at this capacitor, it has a working voltage of 450 volts. If its working voltage is 450 volts, the way these old caps are designed, the surge voltage when it first turns on is even higher than that. So maybe this circuit was designed to run on this kind of voltage. All right, this was very interesting. So looking at this the way it is, I just kind of traced through every wire and tried to get an idea of what this circuit is all about, because you can see there's been things modified in here, like this flying set of wires. I don't think this is factory. This has been changed. The transformer that was installed here is not the correct transformer for the circuit. It may have worked, but there's no way it could have ever worked correctly. Now, unfortunately, I did a lot of looking online and I was unable to find an actual schematic for the Model 200, which is what this is. The closest representation to this I could find was the Precision Model 201A, so that was just a slightly newer model. I think the Model 200 came out somewhere around 1949, 46, I think, maybe 46. And the 201 came out a couple of years after that. Now, I do have one wire still disconnected because I couldn't tell what this component was, and we'll talk about that a little more later. But I was able to disconnect it and measure it and get an idea of what it was. So let's look at the 201A first of all, the schematic for that. If we go down here, and I'll zoom you in. All right. You can see that the tube complement is similar. However, it uses a 6x5 rectifier, so you only need the single 6.3 volt winding. Of course, when you're using the 5Y3, then you have to have the two windings, the 5 volt and the 6.3 volt, for the two different types of filaments. That may be what this was originally, we don't know. And indeed, this is a 6x5 is a glass octal type tube. So the socket would have been correct. So I bet you the original transformer in here was like this. And that 5Y3 that was added because of the different transformer configuration of the replacement transformer that this person used. So that makes sense. You have the 6K6 output, which we still have. You have the 6SJ7 high gain stage, which we still have. You can see all the circuitry here. And the probe input is either a 6AT6 or a 6AQ6. The main difference between them, they're both high gain triodes. The only difference is, I believe the 6AQ, well, let's look them up. I printed them out. 6AT6, as you can see, is a twin diode and a high gain triode, so it looks like this. All right. And if you look at the 6AQ6, again, very similar. All right. And they're not using the diode sections on those. They're just using the triode. They're basically using it as a high gain triode. Whereas our, and this again, this could be wrong, but the tube that we have, and it is properly wired for this tube, is a 6C4, and a 6C4 is a medium gain triode, and there's no diodes elements inside there. So I don't think that really matters very much because according to the schematic, they're not even using the diode elements. They're just using the triode. And really, since this is a grid leak detector, this is just acting as a diode. So really the gain doesn't matter. So you could use any of those tubes as long as they're pinned out properly, and it should work. Now, take a good look at how they did this. The 6K6 is biased with a 600, it's cathode biased with a 680 ohm cathode resistor, and then a bypass capacitor of 50 looks like 50, I think that's a 50 at 25. And the 6SJ7 is cathode biased with a 2200 ohm resistor and a 25 microfarad capacitor bypassing. Just taking some notes here. The input on this is your input select. So if you want to just direct audio, the audio comes directly into the potentiometer and straight into the control grid. That is not a good idea because, of course, if you have a DC level on your audio, you're going to put that right on the control grid. So that's actually not good. So this should have an isolation capacitor, but it does not. Unless this was drawn incorrectly. And then, of course, the output of our probe, if you have it set to RF position, then it's using this, going through this little, it goes through the diode, and that's what strips the audio off of the RF carrier. And then that audio goes through this 0.01 capacitor and in here. So really, this switch, this part of the switch here should be going here, not here. And that might be how in fact it is, but I don't know. I don't have one of these Model 201s to actually check that. It also has a scope output jack, which would be nice so you could see the waveform on an oscilloscope. So that's it. It's a very simple circuit. There's not much to it. Now let's look at what this thing is configured at right now. So I took the time to reverse engineer this and draw out what we have. Very interesting is they did away with the 6X5 and somebody put a 5Y3 in there. And then they had to have two filament windings, one for the 6.3 volts for these guys and one for the 5 volt for the 5Y3. And they're in fact not the correct voltages. The transformer that's in there right now only has a 3 volt winding going to the 5Y3 and a 5 volt winding going to the other ones. And I have a feeling this would have been off of an older set of tubes that use the low voltage filaments. So this is totally the wrong transformer. It has a very high voltage for what this is. And if you take 370 volts, let's do the math. I'll do it right here. 370 times 370 times 1.414 is 523 volts peak. Now, with no load on here, you're going to have a voltage drop across the 5Y3. But even with that, you're going to have way over 400 volts there for a little while. So this is just not correct. So first of all, we have to find a replacement suitable transformer for this. The rest of the circuit, I like it. It's different than this one. One of the differences I noticed is, just like I said, if you look here where the audio goes directly into the volume control and then into the grid, on this one, they have it wired correctly. So if there's AF, you switch it to audio mode over here, and it goes in through here and through the capacitor. If you have IF-RF, it comes off of here through the isolation capacitor into here and then into another capacitor and then down. And They even have an attenuation circuit. So you can see it's either 1-to-1 or 100-to-1. And this is how it's wired, which seems kind of strange to me. You would think that this would be wired down in this part, but they have it wired up here. Unless I looked at the switch incorrectly, I believe this is how they have it wired. I'll have to look at that again, but this would make more sense if it was here. Okay, and then you could bypass that divider network. But anyway, that's kind of what we have going on there. Into a 250K pot. That goes into our 6SJ7, and it's just wired like a high gain amplifier. They actually have the shield of the tube. They're using a metal tube, and they have that tied to ground. They have pins 3 and 5 tied together externally, which is what we want. And then it goes to, instead of a 2200, they have a 2.7K instead of a 2.2K. 25 at 25, 25 at 25, that they kept that the same. The output of the 6SJ7, they have your voltage, and that comes from the power supply here. Goes up through a 470K off of your B+, just like here. And it's kind of, they have the power supply laid out a little bit different. They have extra resistors and so forth. And I think that's to deal with the 6C4. They made some changes in this one. They simplified it. Up to the 470K into our plate. Comes out of the plate with our plate capacitor and couples into our 6K6. And that's just a standard. It doesn't even have a bypass capacitor on it. Now, I don't know if it was removed or something, but no bypass cap on that. And then your output transformer to your speaker. So it's pretty simple. So what I plan to do is I am going to completely strip this chassis out. I'm going to see if I can find the correct, or a suitable, I should say, power transformer for this, which I think I might have one that'll work. And I'm going to totally rebuild this. I'm going to remove all the components and put all new, and see if we can get it to work. So when we're done, I think the only thing that's going to be original to this thing is going to be the chassis and maybe this tube sockets. Okay, the chassis is now stripped down, and you can see we need to straighten it out and clean it and so forth, and we'll do all that. And this transformer looks, you can just see by how the core is wound and everything inside, that I believe this was off of an old radio from either the late 1930s to early 1940s. But this is a radio transformer, and that's probably why the filament windings are strange. The input for this was probably not 120 volts. It was probably closer to 110 because of the era in which it was wound. Mains voltage here in the United States was 110 volts back then, not 125 like we have today. Or possibly 115, which explains why probably this thing gooped out all over the chassis. So definitely not the right transformer. So we'll get rid of that, and we'll find a suitable one, clean this all up, and start from the beginning. Okay, here is a transformer I found in a box in my stash. I have no idea what it is, so we're going to power it up. And just so you know, I have this connected to the dim bulb tester in case there's a short, and to another isolation transformer, all those sorts of things, which is not a big deal, but definitely you want to have this on some kind of current limiting, so if something's shorted, you don't blow fuses and breakers and things like that. All right, let me turn the power on. Turn this on. Actually, I'll turn the power off. I'll connect the leads first. Now, usually when you're looking at power supplies, there are some color codes that usually the transformers will adhere to. So for instance, the red wires are usually your high voltage winding, And if there's a wire with a red stripe, like this yellow and red stripe, that would be the center tap. So we're going to go from this, and we're just going to guess. We're going to go from this to one of the ends, and it should read high voltage. So let's turn it on. And you can see we have 275 volts, which is perfect. That'll give us, after the drop of the rectifier tube and everything, we'll have somewhere around a 350 volt power supply. Now if I remove this one and go to this side, it should be about the same, and it is. So we have, so far we have good B+. That'll be perfect for our project. Now let's go to these, and these most likely are going to be the 5 volt winding for the rectifier tube. So this means this transformer was made to have a tube rectifier versus a solid state. Even though you could use a solid state rectifier, it won't hurt anything, but it has the windings. And sure enough, 5.3 volts unloaded means it'll be about a 5 volt winding when you have the load on it. So the really good news is this transformer will work with the original 5Y3 that he had in there. So we don't have to change that around at all. So these last ones, the green leads, are typically going to be your 6.3 volt filament windings. And they are, you can see that. And this transformer does not have a center tap for the 6.3 volts, and that you would put to ground, and that would help with the hum. But we can make a little hum circuit, anti-hum canceling circuit later on if we want to. But this is going to be a perfect transformer for this project, and it just worked out that way. I looked, and first one sitting in the box. I have a big cardboard box full of random transformers, and I found this one in there. Okay, I just want to see, before we clean our chassis up and everything, if this is going to fit the footprint of the original transformer. So if I put these leads through here, just experimenting here a little bit. And I'll show you what I'm going to do with these leads to make them a little safer and I'll make them last longer. We'll do that later on in the video. This might be a couple part video because we'll go through it slow and test things as we go along, huh? Didn't really think of this turning into a series, but well, that's how it's turning out. So looking at this, it appears, at least, as though it's almost going to fit. Look at that. So really, looks like those original mounting slots are going to line up. The width is correct. So really the only thing we're going to have to move, if you look there, is we're just going to have to elongate or open these holes a little bit bigger here so the wires will fit through. But this transformer will drop right into the footprint of the original one that came with it. Great. All right, so a little bit of elbow grease, cleaned it up, and this polished up really well. Now, the transformer, that old transformer, the overheated and the wax melted out of it and melted all over the chassis. The best way to clean that off is with a heat gun. You take the heat gun, you heat up the chassis real hot, and the wax just melts and you can wipe it right off. So that's what I did. This little bit of staining is all that's left, and there's no corrosion or rust. Cleaned up really well. And pleasant surprise, look at these tubes. Yeah, they're Joint Army Navy or JAN type tubes. Very high quality. And so I think, now of course we're going to have to test them to make sure that they're good, but I have a feeling they're going to be just fine. For the transformer, I'm not going to paint the end bells. There's a little bit of rust on them. You could see just the tiniest amount, but it's not bad. And for these wires, they're starting to get a little bit stiff. You can retreat these wires a couple ways if they're not broken or cracked. The first thing you can do is you can use paraffin. You have to melt it till it's liquid, which is really hot and it smells bad, and then you can just dip the whole thing in and it'll actually reconstitute these wires as long as they're not cracked or broken. See how nice these ones are? The other thing is what I'm doing, and that is to use this rubberized heat shrink, and it's clear. So you take this and you just slide it right over the end of the wire, like so. And when you get it almost all the way to the end, cut it off flush, like so, and then push it down the rest of the way. And then just hit it with the heat gun. And that'll just guarantee that these wires are never going to crack or dry out or fall apart. This stuff's really strong, and it's very, very hard to... This type of heat shrink, I bought it on eBay. It was like some kind of factory surplus. You can see it, how it just stretches and it won't break. And it's very hard to cut with a knife. You have to use scissors or clippers to cut it. So it's really good. It'll last forever for the most part. So I'm going to coat the rest of these wires. And I think I'm going to call this this video, I'm going to call it right here. We're going to stop. This is a good stopping point. When we come back on the next part, we'll get everything started to mount up and we'll start soldering all the new components in. These cleaned up, so we're going to just reuse them. They're good. Everything's good. Other than, you know, the old components sitting over there, we're not going to reuse those. So, until next time, I wish you all peace, joy, happiness, and good health. And we'll see you next time where we start to build this thing. Take care, everyone. Bye-bye.